Rockets and propulsion. Propulsion basics. Propulsion basics. Fundamental principle behind rocket propulsion is Newton's action-reaction law. For every action there is an equal and opposite reaction. Escaping exhaust gas of the rocket motor drives the rocket in the opposite direction with an equal force, forward thrust. This is equivalent to the forward momentum of the rocket being the same as the momentum of the exhaust, but in the opposite direction. Momentum equals mass x velocity equals mv. Propulsion basics. Momentum equals mass x velocity equals mv. Momentum forward equals momentum rearward equals mass rocket x velocity rocket equals mass exhaust gas x velocity exhaust gas. Mr. Vr equals MEV or Vr equals VME/Mr. Since the mass of the rocket is much greater than the mass of the exhaust gas, the velocity of the exhaust gas must be much greater than the forward velocity of the rocket. Thrust and momentum are not the same. Propulsion basics. Thrust and momentum are not the same. Thrust equals force equals weight, in dimensions. Momentum times mass flow rate, 1 per seconds, has the same dimensions as thrust, mass length/time 2. For measuring rocket thrust, we therefore need exhaust momentum time exhaust mass flow rate. The size of a rocket roughly determines its thrust, or lift capacity. Propulsion basics. Mass flow rate is the amount of fuel that is consumed, or combusted, and expelled as exhaust. Larger rockets consume more fuel than smaller rocket in the same time interval. Larger rockets produce more thrust than smaller rockets. All very obvious? The size of a rocket roughly determines its thrust, or lift capacity. Thrust is determined by mass flow rate and exhaust velocity. Propulsion basics. Propulsion performance is measured primarily as thrust and exhaust velocity. Thrust is determined by mass flow rate and exhaust velocity. Exhaust velocity is a measure of thrust efficiency. Higher exhaust velocity equals higher thrust efficiency. Rocket propulsion types. Rocket propulsion types. Chemical. Liquid propellant. Single, mono, combined fuel and oxidizer. Dual, bi, separate fuel and oxidizer. Solid propellant, combined fuel and oxidizer. Compressed gas. Unheated. Heated. Electric. Ion. Electrothermal. Nuclear. Solar pressure. Simplest propulsion type is compressed gas. Propulsion types. Rocket propulsion. Simplest propulsion type is compressed gas. Simple. Inexpensive. Inefficient, low exhaust velocity. Low energy content. Used on small satellites. Balloon is the simplest example. Most common rocket propulsion type is the solid rocket. Propulsion types. Most common rocket propulsion type is the solid rocket. Simple. Inexpensive. Modest exhaust velocity. Can be scaled from small model rocket and fireworks to large solid rocket boosters used on the Space Shuttle. Single use. Used primarily for first stage boosters and separation motors. Propulsion types. Large rocket engines used for most launchers are liquid bipropellant engines. Complex. Relatively expensive. Higher exhaust velocity. Difficult to scale from small to large. Can be restartable and or reusable. Liquid monopropellant engines. Propulsion types. Liquid monopropellant engines. Simple. Relatively inexpensive. Modest exhaust velocity. Can be scaled up to moderate thrust. Often restartable and used in a variety of roles, attitude control, orbit booster, deorbit motor, etc. Electric propulsion engines. Propulsion types. Electric propulsion engines. Relatively complex. Expensive. Very low thrust. Very high exhaust velocity. Usable only in space, vacuum. A developing technology, although used on interplanetary boosters and for satellite station keeping. Electric propulsion, ion engine. Propulsion types. Electric propulsion, ion engine. Electric and or magnetic fields used to accelerate charged atoms, ions. Heavy nuclei better than light nuclei, She commonly used. Extremely low thrust. 10 to 6 N, 0.01 N. Very high exhaust velocity. 10 to 100 times chemical rocket exhaust velocity. Electric propulsion, electrothermal, heated gas. Propulsion types. Electric propulsion, electrothermal, heated gas. Electric current used to heat cold gas. Heating reactive or inert gas increases exhaust velocity and thrust. Low to modest thrust. Moderate exhaust velocity. Resistojet, electric heater. Arc jet, electric arc heating. Other electric propulsion types include magnetoplasma-dynamic engine, variable specific impulse magnetoplasma rocket, VSMR, engine, nuclear ion engine, heated gas by hot nuclear reactor core. Nuclear reactors used to heat a cold gas to very high temperatures. Propulsion types. Nuclear propulsion. Nuclear reactors used to heat a cold gas to very high temperatures. Hydrogen gas is the most efficient propellant. High exhaust gas velocities. Heated gas by hot nuclear reactor core. Nuclear ion engine is a variation with greater efficiency. Nuclear propulsion, NERVA program, 1957 to 1972. Propulsion types. Nuclear propulsion, NERVA program, 1957 to 1972. Solar pressure propulsion. Propulsion types. Solar pressure propulsion. Solar photon pressure can be used for propulsion, solar sailing, with certain limitations. Low thrust. Low payload mass. Very large reflective sail needed. Operable only in vacuum of space. Limited to inner solar system. Prototype launches failed, but several are being readied for flight. Rocket propulsion performance. Propulsion performance. Lift/payload performance. A rocket's lift or payload performance is a function of three measures. Thrust. Thrust efficiency, ISP. Thrust duration. These three components also determine the total propulsive energy of the rocket and its propellants. Propulsion performance. Thrust. Thrust is a measure of the forward force produced by the rocket. Thrust has the same dimensions of both force and weight. Thrust units are typically lbf, meaning force in pounds, or in newtons, or kgf meaning kg force. Thrust is proportional to exhaust momentum times exhaust mass flow rate. Thrust can be increased or decreased in some rocket motor designs by increasing or decreasing the propellant flow rate. Propulsion performance. Thrust. Three factors dominate thrust performance of the chemical rocket motor. 1. Fuel flow rate. Higher fuel flow rates increase forward thrust. 2. Pressure difference between internal nozzle pressure and external, ambient, pressure. Maximum pressure difference is in space, vacuum pressure. 3. Exhaust velocity. Higher velocity produces greater forward thrust. Propulsion performance. Thrust efficiency, specific impulse, ISP. Specific impulse is a measure of the thrust produced for a given fuel weight flow. An equation expressing ISP in relation to the thrust produced and the fuel consumed, fuel flow rate, would be ISP equals thrust produced, fuel weight flow rate, dimensions and units are seconds, propulsion performance. Thrust efficiency, specific impulse, ISP. ISP value is a measure of how efficient the propellant, or engine, is converted into thrust. ISP could also be described as the burn time of a fuel for a specified mass at a specified thrust. A fuel with an ISP that is 2 times another would burn twice as long with the same thrust. Propulsion performance. Approximate ISP ranges. Very high. 1000 to 10,000 seconds. Ion and plasma engines. High. 350 to 500 seconds. Liquid bipropellant, liquid fuel plus liquid oxidizer. Moderate. 200 to 350 seconds. Solid fuel or liquid monopropellant, liquid fuel combined with oxidizer. Low. 0-200 seconds. Cold, compressed, gas. Propulsion performance. Engine. ISP. Thrust. Space Shuttle Main Engine, SSME. 453s, VAC, 363s, sea level. 233,295 kgf, 513,250 lbf, 2.3 meganewtons, VAC. Space Shuttle Solid Rocket Boosters, SRB. 269s, VAC, 237s, sea level. 1,500,000 kgf, 3,300,000 lbf, 14.8 meganewtons, sea level. Saturn V F1 first stage engine. 260s, sea level. 681,180 kgf, 1,500,000 lbf, 6.7 meganewtons, sea level. Propulsion performance. Specific impulse that is a measure of thrust efficiency is also proportional to exhaust velocity. An approximation of the relationship between thrust efficiency and exhaust velocity is Vexhaust equals GISP, where G is the gravitational acceleration at the Earth's surface equals 9.8 meters/s2. For example, a rocket engine with an ISP of 300 s would have an exhaust velocity of 300 s x 9.8 meters/s2 equals 2,940 meters per second, 6,580 miles per hour. Propulsion performance. For chemical rockets, exhaust velocity is influenced primarily by the following factors. Exhaust gas molecular weight, lower is better. Hydrogen is one of the optimum fuels. Combustion temperature, higher is better. Limited by the combustion's chamber strength. Combustion chamber pressure, higher is better. Specific heat ratio, chemical energy available to convert fuel into exhaust gas based on the reaction chemistry of the fuel and oxidizer. Some fuels are better than others. Exhaust nozzle geometry maximizes exhaust velocity using both the kinetic and potential energies of the exhaust gas flow. Propulsion performance. Propulsion performance. Exhaust nozzle. To optimize the exit velocity in a chemical rocket, subsonic gas will increase speed if flowing through a converging exit nozzle, decrease flowing through a diverging nozzle. Supersonic gas will increase its flow speed through a diverging nozzle, decrease flowing through a converging nozzle. Maximum exhaust velocity comes from a subsonic flow through a converging interior nozzle with supersonic flow through the exterior diverging nozzle. Also important in optimizing exhaust velocity include the nozzle's convergent and divergent angles, and the throat to exit area ratio. Propulsion performance. Exhaust nozzle. Expansion of the exhaust from the combustion chamber and the nozzle throat should ideally conform to an even flow into the outside gas, or vacuum. For conditions showing correct expansion, under-expansion, and over-expansion from the nozzle with respect to the ambient air/vacuum are shown on the right. Under-expanded, top, Ideal. Overexpanded. Far overexpanded, bottom. Propellants and motors. Propellants. Propellant selection is important, not only for combustion energy and exhaust gas velocity, but also for density, storage, handling, and cost. The simplest rocket fuels are solids, which consist of a combined fuel and oxidizer compound that is stabilized into a fast-burning propellant. The solid fuel is generally cast in the combustion chamber as a unit. Liquid propellants called monopropellants can also have a combined fuel and oxidizer compound. The single, mono, liquid propellant is simpler and much less costly to store and handle than cryogenic propellants, liquid propellants. Propellant choice is not only based on performance and density, but also on a variety of characteristics that include important safety and handling criteria, some of which are: specific impulse, ISP, cost, toxicity and health hazards, explosion and fire hazard, corrosion characteristics, handling safety, propulsion system computability, freezing/boiling point temperatures, stability, heat transfer properties, ignition, flame and combustion properties. Propellants, common types of liquid propellants. Oxidizer. Fuel. ISP, theoretical. Liquid oxygen, LOX. Liquid hydrogen, LH2. 477S. LOX. Kerosene, RP1. 370S. Monomethylhydrazine. 365S. Methane, CH4. 368S. Liquid ozone, O3. Hydrogen. 580S. Nitrogen tetroxide, N2O4. Hydrazine, N2H4. 334S. Hydrogen peroxide, H2O2. Monopropellant. 154S, 90% H2O2. H2O2. Hydrazine. Fluorine. Lithium. 542S. Liquid propellant engine basics. Liquid bipropellant engine diagram showing the major elements, and several of the thrust parameters that include exhaust and ambient pressures, P and PO, exhaust velocity, V, and mass flow rate, dm/dt, courtesy NASA Exploration. Solid propellants. Solid rocket propellants contain a variety of chemicals in addition to the basic fuel and oxidizer, part for stabilization and part for performance. Solid fuels used for larger rockets are composite mixtures containing separate granulated or powdered fuel and oxidizer, with a chemical binder, a stabilizer, and often an accelerant or catalyst added for improved performance and stability. The final mixture of solid fuel used today is a dense, rubber-like material that is cast into the combustion chamber. Solid propellants. The cast fuel has a central cavity to allow burning throughout the length of the rocket motor, in shapes that can be anything from a simple cylinder to a star. Solid rocket fuel is typically identified by the type of chemical binder used, either HTPB or PN. Hydroxyl terminated polybutadiene, or HTPB, is a rubber-like binder that is stronger, more flexible, and faster curing than PN, but suffers from a slightly lower ISP, and uses fast curing, toxic isoconates. Solid propellants. Polybutadiene acrylic acid acrylonitrile, PBAN, has a slightly higher ISP, is less costly, and less toxic, which makes it popular for amateur rocket makers. PN is also used in the large boosters, including the Titan III, the Space Shuttle SRBs, and NASA's new Constellation Ares I and Ares V launchers. HTPB is or has been used in the Delta II, Delta III, Delta IV, Titan IVB and Ariane launchers. Hybrid rockets. Hybrid chemical rocket motors, motors with solid fuel and liquid oxidizer, are used for intermediate-sized boosters. The most familiar hybrid engine is the one used to power Bertrand's Spaceship One, test article shown below. The cast solid fuel core is contained in a combustion chamber. Nitrous oxide stored as a liquid is injected over the solid fuel core. The oxidizer flow is used to start, regulate, and stop the combustion process. Rocket stability. Rocket stability. Two types of stability of a rocket are needed for its successful flight. Static, stability during initial launch. Dynamic, stability during powered and unpowered flight. Static stability. The force of thrust, or even simple gravity on a rocket or on an upright pencil produces stable lift, unstable lift, or a neutral stable lift. An analogy is an upright pencil with a force of gravity pulling downward which is equivalent to a propulsion thrust pushing upwards. The rocket must be stabilized in its initial launch or the force of thrust will immediately rotate the rocket, pencil. Upward force below the center of mass is unstable. Upward force above the center of gravity is stable. Used on larger rockets and missiles, Atlas missile shown on the right. Rocket stability. Static stability. Passive. Traditionally provided on very small rockets with a guide rail attached to the launch pad and a guide attachment on the rocket. Active. A guidance control system creates thrust vectoring of the rocket exhaust for launch. Used on larger rockets and missiles, Atlas missile shown on the right. Can be provided by control of the main engine thrust, or by smaller augmentation guidance engines. Requires aerodynamic force aft of the center of mass. Rocket stability. Dynamic stability. Passive. Aerodynamic fins create restoring force to align the rocket in the direction of motion during flight. Requires aerodynamic force aft of the center of mass. Dynamic stability. Rocket stability active. A guidance control system creates thrust vectoring of the rocket exhaust for launch. Used on larger rockets and missiles. Can be provided by control of the main engine thrust, or by smaller augmentation guidance engines. Soviet Road 107 shown on the right with 4 primary thrust engines and 4 small outboard vernier guidance thrusters. Modern rocket development. V-2 early missiles. The German V-2 developed by the Nazis in WW2. Alcohol fuel, ethanol 75%, water 25% for cooling and stability. Liquid oxygen oxidizer. Employed double-wall combustion chamber. Inner cavity allowed fuel to circulate to cool combustion chamber. 55,000 lbf thrust. 24,958 N. Redstone early missiles. Developed by Werner von Braun and the Army Ballistic Missile Agency, ABMA. Intermediate Range Ballistic Missile, IRBM. Used similar design features of the V-2 with improved performance. Engine design by North American, Rocketdyne. Na 75-110. Based on Navajo cruise missile engine. Alcohol fuel. Liquid oxygen oxidizer. Payload 6,300 pounds. 78,000 to 83,000 lbf thrust, Jupiter missile early missiles. Intermediate Range Ballistic Missile, IRBM. Combined Army-Navy project. Limited use as IRBM missile. Navy rejected design for submarine missiles. Converted to use by NASA for the early interplanetary missions. Juno 2. Juno I was Redstone spacecraft launcher. 150,000 lbf thrust. Thor missile, IRBM, early missiles. Initial intermediate range missile for US and European deployment during the Cold War. Single Rocketdyne LR-79, ST-3, engine used later on Atlas. 150,000 lbf thrust. Single stage missile was augmented with multiple stage for increased payload and range, and launching first reconnaissance satellites. 4-stage version later renamed Delta, fourth letter of Greek alphabet. Delta booster now a family of launchers. Early missiles. Delta rocket family. Atlas ICBM first American intercontinental ballistic missile, ICBM. Early missiles. Atlas ICBM. First American intercontinental ballistic missile, ICBM. USAF project. Still used as commercial launcher. Medium and heavy lift versions. Atlas V heavy lift booster uses Russian Rod 180 engine. Liquid oxygen, LOX, and kerosene first stage. Used 3 primary engines on original ICBM design sustainer, central. Early missiles. Atlas ICBM. Used 3 primary engines on original ICBM design. Sustainer, central. Steering and augmented thrust engines outboard. Later used for Mercury orbital missions. Used for Gemini's Agena target vehicle launch. Developed into family of launchers, Atlas rocket family, plus Titans. Early missiles. Atlas rocket family, plus Titans. Navy Viking missile early missiles. Developed by Naval Research Labs as a missile prototype. Used Reaction Motors Company XLR-10RM engine. First to use integrated tanks and structure, monocoque. First to use thrust vectored engines. Used as first stage for Vanguard rocket. First satellite launch attempt. Alcohol and liquid oxygen propellants. Titan missile early missiles. Developed originally for the Air Force as a backup ICBM to supplement the Atlas. Original Titan I design used RP-1, kerosene, and LOX. Later Titan II used nitrogen tetroxide, NTO, and unsymmetrical dimethylhydrazine, UDMH. Titan III and Titan IV used solid rocket boosters to augment thrust on first stage. Prototype for SRBs used on Space Shuttle. Heaviest lift launcher before Delta IV Heavy. Early missiles. Titan missile. Titan III and IV used for both military satellite launches and civil interplanetary launches. Heaviest lift launcher before Delta IV Heavy. Current rockets. Current rockets. Delta launcher family. Current rockets. Atlas launcher family. Delta IV Heavy used for spacecraft launches. Rocket stability. Delta IV Heavy used for spacecraft launches. Atlas V Heavy to be used for Orion capsule tests. Newest launcher is NASA's Heavy Lift Launcher Designated Space Launch System, SLS, Space Launch System, SLS, 3-stage booster payload capacity. Rocket stability. Space Launch System, SLS. 3-stage booster. Payload capacity. LEO 70,000 kilograms to 129,000 kilograms. 150,000 pounds to 280,000 pounds. First stage, 5-segment SRB boosters. Second stage, core, LOX LH2 fueled RS-25E engines, 5. Third stage, 1 RL-10B2 engine or 3 J2X engines. First stage, 9 Merlin engines. Second stage, 1 Merlin engines. Rocket stability. Falcon 9 rocket. 2-stage booster. Payload capacity. LEO 10,450 kilograms, 23,000 pounds. First stage, 9 Merlin engines. Second stage, 1 Merlin engines. Propellants LOX and RP-1, refined kerosene.